Here we have a sheet of metal. This metal doesn't need to be a magnetic material, any metal will do. Next, we bring in a permanent magnet, moving it towards the sheet of metal with some velocity. The direction of the magnetic field from the magnet is directed away from the North Pole. Lenz's law states, the induced EMF is always in such a direction as to oppose the change that caused it. Although the precise wording changes slightly from book to book, the consequences are always the same. In this situation, the induced EMF will in turn induce a current that gives rise to a magnetic field that opposes the change that caused it. In other words, the changing magnetic field is being caused by a magnet moving towards the metal sheet, so the induced magnetic field will try to repel it, establishing a magnetic field in the opposite direction, effectively turning the front of the sheet of metal into a North Pole. From this, we can now determine the shape of the electric current induced as well as the direction, remembering the rule for the end of a solenoid that a North Pole is caused by an anti-clockwise current. These currents are known as eddy currents. Eddy currents can become extremely large due to the low resistance pathways that they can occur in. In turn, these currents can cause significant heating. Now let's take a look at an application. This effect is often used in roller coasters and large vehicles and is called magnetic braking. In the video, I will demonstrate this in action. Have a think about the questions raised during the video, as they will feature in a follow-on task for today's lesson. So what I have here are two coils. You can ignore the number of turns on the coils. I'm not actually interested in that at the moment. They're both attached to a DC power supply. The DC power supply is not currently switched on. Also what we have here is we have an aluminium pendulum that, if I'm careful, I can swing without it clattering on the electromagnet. So we're effectively going to be using this as an electromagnet, which is why I'm using DC, not AC. Right. So this is the principle of braking. Let's take a look at this side first. One end is solid, the other end has teeth in. Let's do the solid side first. Turn the power on. Let's do that again. Turn the power on. Hopefully you saw some braking there. What I'll do now is I'll turn it around so that we've got the side with the teeth on. And set it oscillating again. Turn the power on. Much less of an effect. I hope that you saw that. So let's compare again. So there is still an effect. It still oscillates 3, 4, 5, 6 times at least before it comes to a stop. And just to prove that, let's just turn that back around again just one more time and do it with the solid side. Almost an instant stop.
My favorite tabletop demonstration of magnetic braking is to swing a magnet toward a chunk of copper like a wrecking ball. The magnet loses all of its momentum at the very last moment in a way that almost looks supernatural. It reminds me of a scene in the second Matrix movie where Neo stops bullets in midair. What's really happening is of course the same thing that has happened in my other examples. The magnet's momentum is slowed by opposing magnetic fields generated by the flow of electrons in the copper. And since the electrical energy isn't being collected by a circuit for any useful purpose, it dissipates into the lump of copper as heat. So the copper actually gets warmer every time I swing the magnet toward it, but by such a small amount that measuring the change would be very difficult.
There you could clearly see the braking effect of the induced eddy currents. Now, a conundrum. For the earlier magnetic braking demonstration, I used a demonstration transformer as my electromagnet. Watch the following video and think about why the iron core used in the transformer is a laminated iron core. Let's take a closer look at what makes up the main body of the transformer, the demonstration transformer. If you notice, it is an iron core, but it is a laminated iron core. In other words, laminated meaning in lots of little sheets of iron there. Have a think about why that might be the case. Why is it not just a solid iron core? Why is it lots of laminated sheets of iron all glued together? There are far too many applications of eddy currents to go into here, but I would like you to consider two after this lesson. First, an induction hob. These are particularly useful in that they cook food in a pan but are cold to the touch. How do they work? And secondly, metal detectors. How can you use the idea of eddy currents to explain how metal detectors work? This is your final task for the lesson.